So I will start with a couple of applications that we worked in the visual recognition group. One type of problems we worked on faces. And this example is about some non-standard things in face analysis. So people have worked on facial recognition for decades. You have heard about the results, you know about Big Brother, but there is a different type of maybe not so oftenly studied problems, like can I detect whether someone is lying in a video? This is quite useful. And I'm not sure what will happen if I start pressing the buttons. Maybe the videos will start. Something is happening. So maybe if you notice the guy in the top left when the video starts, there's some sort of short flicker in his eye and then maybe raises his eyebrows. And these are some things, this is a micro-expression. Micro-expression lasts like 200 milliseconds. You have no control over it. And it gives you sort of direct access to the emotional state of the person. Probably most of you know that it's fairly easy to monitor your heart rate just from standard video with fairly high precision. And altogether this led us to believe that maybe we can check whether someone is lying. It turns out that in machine learning we need what? A lot of training data, and that's not so much available. Like download videos with people lying, as opposed to download videos to people telling the truth didn't work. So we switched slightly the topic. And we said, okay, let's check whether we can detect whether the person knows an answer. Maybe these days you don't have to examine students at the university. You just pose the question, ask for 2 seconds, look at their expression, and you send them home with the correct grade. That was the idea. So we took this show, Who Wants to Be a Millionaire? You have lots of recordings online. You know whether the person answered correctly or whether we asked for help. You can actually get that automatically from the annotations of the... and it turns out that you can predict from the first few seconds quite reliably whether the person knows the answer. So maybe these two slides are in this direction, that there are many things in facial analysis that people have not studied so extensively as recognition, but things like, do the people understand what I'm saying? Do they pay attention? We wanted to do an experiment like that in my course on machine learning, but the students did not approve. So, and here I didn't even try to ask for the approval. Now, yes, machine learning is super efficient in dealing with faces where we have enormous amount of data. So this is an example of work where you see the input on the left, the super resolution and the ground truth. So it means that the super resolution, actually it means the information in the low resolution is giving such a precise conditional probability on the faces in high resolution that it's close, it's distinguishable but not much. And you can play with deep fakes where hair is, for instance, a tricky thing because it's not so easy to switch it between subjects so that it really looks natural, but it's another thing that we worked on. Now we'll switch to another topic before going to the lecture itself. We looked at temporal super resolution. So you might have videos, and you see the video on the top, which is from a standard camera. The table tennis ball is moving fast, and there is some interlacing effect. And from the blur and the motion of the ball from a single camera, you can estimate the deep blurred shape of the ball. You can estimate the trajectory, and from that, you can generate a video of sort of arbitrary temporal smoothness. So if you know the trajectory and you de-blur what you see, you can do something like the video at the bottom. We wrote a paper on this, and someone pointed to me, my student Dennis, said, look, things are happening on Twitter. So apparently on Twitter there was a video for 5 years, from 2016, when they were saying, this is the video that really persuaded me that this is a UFO. Must be UFO, nothing else. Long thread. And then someone says, we try this method for tracking fast-moving objects with the blurring, and in the end, I'm not sure whether these videos play. Some of these are the videos. This is a video. It's really fast-moving because the bird was close to the camera, but I'm missing and in the end, you see that probably at the bottom there. Oh, the video is there in the I don't know how to, because I don't have a mouse, I don't know how to start the video in the corner. But after the blurring and tracking, it turns out to be a falcon. And after 5 years, the people who were really persuaded that this is a fast-moving UFO, they recognize what it was. So still, in vision, you have open problems, and all of these things are closely related to deep nets. One more thing which I worked on is 3D reconstruction and object detection from a single view. These are mainly topics if someone wants to talk to me afterwards. And now I'm switching to the real topic of the talk, which was some ignored issues related to deployment of neural networks. So many of the problems in computer vision, natural language processing are now treated with deep nets and transformer nets. And still, there is something we can learn from old theory to improve their deployment. So probably all of you know that these days, if you have a problem, say, of a predictive nature, you start by collecting a large collection of data, picking the class of your model, the structure of the deep net, and then you pick some loss function, and you take an optimizer, usually stochastic gradient descent, to minimize the expectation of this loss. Now, SGD gradient requires the loss function to be differentiable. Now, in the past few years, we looked at the problem where during deployment, which is called test time, maybe in lab settings, you get different data, and in fact, the quality of your solution depends on an evaluation metric. So this is what the user says. This is not the same thing as this loss function, and it's actually very rarely the same thing. And of course, the tricky part is if the evaluation metric doesn't match the loss, then anything can happen. And people often ignore the evaluation metric and pick some loss. So, and if the evaluation metric is non-differentiable, which is very common, then it cannot be used as a loss function, and something has to give. The classical approach is that, okay, maybe we want to minimize the number of errors, but that's non-differentiable, so we pick some loss function which works somewhere well, we plug it in, and we hope for the best. Here we have the gradients, but we have a mismatch between the evaluation metric and the loss function. So I'll show 3 examples where this can happen. So a very simple example, a very old problem, image compression. Image compression is nice in the sense that you can have only images you want to compress without any human annotations. It's sort of a self-supervised method. You have the input image. You want to have the reconstructed image. This is the compression that will be sent or stored. And what you want is to have some high compression rate and small distortion rate, and the balance between these two will be somehow controlled by the constants alpha and beta. Maybe you can have just one for the ratio. Now, so what is the trick here? Like, what is the problem? We have infinite amount of data because we can train on any image our encoder and decoders. We have the loss function, but is this the evaluation metric? Now, when it comes to rate, it's obvious. Yeah? And we want the storage space is given, but what about the distortion? So here, probably nobody would, at this time, dare to measure this by square, this difference between RGB values of the pixels, the sum of squares. But you have all sorts of, the commonly used characteristics are things like PSR, peak the signal-to-noise ratio, structure similarity index. But what you really would like to optimize is the human perception of similarity, or maybe human perception of distortion. And it turns out that this is very difficult to obtain. And if you look at examples of compressing this original, the methods published recently have a better and better similarity, but if you look at this one, it looks worse than the JPEG. So this just highlights the problem of evaluation metric not clear and definitely not the loss. Another problem which we worked on, and that actually triggered our interest in this, is the text recognition in the wild. So in the wild means we are not talking about scanned documents, we have an image of a scene, and there is some text observed at some angle, and you want, in the end, the transcription of the text here. That's your prediction. And now, if you are, let's say, doing this end-to-end with single network or maybe with some complex pipeline, all the parameters of these modules should be optimized with respect to reasonable loss. Now, the most common loss used is cross entropy. So this would be for the text, for the number of letters, 1 to L, for all the possible characters in your alphabet. This thing is the label, and this is your prediction. And this expression is called cross entropy, but when you are transcribing text, you don't care about cross entropy. Yeah? What you care about usually is the edit distance. It's something like how many spelling mistakes you make. In fact, that's probably not even the thing which you care about. Maybe what you care about is what is left as a mistake after some spell checking, which actually in the wild is quite difficult because that's where you have names of shops and all sorts of proper names. So this just shows the difference between the two metrics. Okay, so one is the loss, and maybe the proxy loss, which we can say is this cross entropy. So the first example is the image. This is the image you would like to read. The letters are A, B, C, and what you see in the table is this is the ground truth, A, B, and C, and this is the softmax, the output of the, let's say, output of the network for the first, second, and third letter. So this one has correct output. So if the network operated like that, and we would take the maximum in every column as our prediction of the first, second, and third letter, we have 0 error. So there you see nothing here. But of course, the cross entropy, unless this was 1, 1, 1, would not be 0. On the other hand, here, this would be a different output of another, maybe the same network with different parameters, not so well trained at the moment. It makes a mistake here. It thinks the first letter is C, and here the edit distance is very high. It's 2, and the CBC entropy is some number which is higher than original but not so high. Now on in the last example, exactly the same edit distance, 1 letter wrong, or maybe and this thing is higher. So you see that somehow it is correlated, but what we care about is not what is used in training usually. Now, the edit distance is an integer. It's a value of 1. Yeah, 1 letter is wrong. So this is 0, 1, or 2, so of course it's not differentiable. Third example is even more involved. That's the problem of retrieval. So in the retrieval problem, we have a query input, that's a single image, and then we have a large collection of images. I show 4 here, but usually you have millions, or maybe hundreds of thousands. And what you want to do is to retrieve some short list of k images, and those that are relevant for the query. So that could be similar to the query or from the same category. So if you had this type of output and you would like to have 2 outputs, you would have a perfect result. Now, okay, so how you train this thing is you take triplets. So think about a triplet like this, or maybe the query and 2 images, and what you put in the metric is something similar. Well, it's shown here. You say, okay, take the query, take the distance to the, say, positive example in your triplet. so that would be another bike. So maybe I put distance of what distance? We would like to project every image into a metric space through a deep network so that distance between objects of the same type are small and distances between objects of different classes are larger. So we train this by forming triplets of 2 positives and 1 negative. Negative would be maybe the cup. So if the distance, now, okay, if distance is 0, it means that the negative and positive example are equally distant from the query, which is not good because you would like to have some alpha margin. If your difference is bigger than the margin, smaller than the margin, you are fine. Else, you pay here a price, and the price is proportional. Of course, in terms of evaluation, you only care whether the bike is before the cup, not after the cup, but you had to do some differential. To train something, you need something differential, and this is this hinge loss. So I will now go through 3 examples, example of methods where you can do something better than say, I give up. I cannot use the non-differentiable loss function. I will use some proxy which is commonly used and hope for the best. So the first one is about learning surrogates. So far we use the word proxy. Proxy is some function that you chose because it worked someone's well in some other problem, but it has nothing to do with my problem. So the first thing we tried is this. We say, very often in deep learning, people have been surprised how much you can do with embedding vectors of high dimensionality. So the idea is simple. We have a ground truth and the output of the classifier or predictor. Maybe this could be a string. Think about a string. What you want to approximate is the edit distance, something integer. So we propose to train, this is Siamese, so this is mapping a string to some high dimensional space in which L2, classical Euclidean distance, will be approximating the evaluation metric. So for 2 identical strings, this must be 0. For something like with 1 letter difference, the embedding could be, has the property. Now, for those who know the Levenstein metric on strings, and this is computed by dynamic programming, it's a fairly sort of easy to understand, but not so easy to compute thing. And you say, okay, but instead of this algorithm, and I will be able to somehow send this data to some high-dimensional space, and it will do the same thing. But okay, here we do SGD, it's stochastic anyway, so if it's highly correlated, I'll be fine. I will not be doing that exactly. So what we are saying, when you are training your model to recognize strings, you should also learn at the same time a surrogate, something which tries to approximate the loss function, the evaluation metric you really care about. Okay? So, fine, this turns out to be, here we say that we would like to approximate the non-differentiable evaluation metric in a least square sense. For some technical reasons, we try to keep this gradient small, otherwise it becomes unstable. And the code becomes like the process is 2-stage. First, learn the surrogate. Perhaps here we use you start by using the proxy. So you train your recognizer by the proxy loss, say cross entropy. Then you learn the surrogate. And finally, you learn your recognizer using the surrogate with the correct loss function, which has been trained to be very close to the evaluation metric of the user. And it leads to maybe 40% improvement it depends on the situations, on which data set, and so on. But with the one example, I forgot normalized edit distance, on all other, on one data set, it improved every single result. So in some sense, you can say, okay, these results, why is this 39 here and the numbers are here smaller? Because it's the reduction of the error. So here, for instance, it's very significant. But if you are doing something again and again and again, such differences are important. Also, if it's like a Kaggle type of contest, it's the difference between being the winner and maybe somewhere in the middle of the pack. Okay, fine, same thing. So now, I said that to start this, we had to start with a trained classifier. We couldn't start from scratch. Give me the model, not trained at all, and learn the surrogate at the same time as the model for prediction. That turned out to be unstable. So at the beginning, you see that the predictor, this is the real eddy distance, and this was the predicted one, was underestimating the error. And we didn't know what to do to stabilize the calculation. So in the end, we proposed a system that says we will learn the classifier, the text detector and classifier, at the same time as the approximation, the surrogate. But if for samples where the approximation is poor, we will replace the error of the approximation with a constant function, essentially making the gradient 0. Maybe what is interesting here is to get you an idea how you represent the text. So it seems like how can I match, it's difficult to imagine how can text be mapped into high-dimensional vector, but the text is actually represented by a matrix. So if the ground truth is a matrix which has 1 in every column. So the first column says the probability distribution on the characters for the first one. So maybe this would be A. Maybe the second character is D, and so on. The output is soft from the detector. So the first character could be A, but many others. So now the coding, the mapping of the string. Well, this is like a probability on strings. This can be seen as one string, or a special case of probability on strings where every letter collapsed to one possibility. So you are actually mapping this matrix to some high-dimensional space where the L2 is close to the eddy distance. And again, it is still improved on our previous work by about 10%. Now the recall. So we talked about the problem of image retrieval, and so far we didn't talk about the object detection non-differentiable problems. We just talked about scene recognition, but these metrics are decomposable and non-differentiable. Decomposable means that you take one string and you want to measure the error, and that depends on the string. But now, in this problem with retrieval, the evaluation metric is non-decomposable and non-differentiable, so one prediction does not tell you whether it's good or bad. You have to take into the evaluation into account the whole set of responses. So, because your rank depends on every other image in the collection in which you are doing the image retrieval. So this becomes even more challenging. So just to recap, I will introduce the recall metric, evaluation metric of image retrieval. So in this example, we have a query, and we retrieved we measure the distance between the query and every object in the data set. Of course, this has to be done somehow fast. You don't do it through every, but let's say for simplicity, we think about that. So then we take the distance, or maybe similarity score. This is done by similarity scores. We sort it. And now, how good is this sorting? Imagine you have 10,000 results, here we have 4. So the sorting is good if the green things, the relevant things, are close to the top of the list. So, and the recall at K is the percentage of correct answers in the top k. So recall at 1 in this is the same thing as accuracy of a classifier, and that's here it will be 1 because the first one is correct. Now recall at k, here is 1/2 because there's 1 green, 1 red, and here recall at 3 is 2/3, recall at 4 is 1/2. So what you would like to have is recall at k close to 1 for some relevant set of k's. So perhaps police are looking for a suspect, and what they say, okay, we have the whole huge database of people, show us a screen of 16 pictures, that's what I can easily see, and recall at 16 is all we care. Either the person who is sought is there, or it's not there. So the k depends on the application. So now maybe I will do it here. The essential result or the insight in here is that although we are ranking, then the rank can be expressed as a sum of this h functions, which is the Heaviside step function. So if you want to calculate the rank of this bicycle in the collection of 4, you can compute the difference between the 0.7 and 0.6, 0.9, 0.8. And if the difference is negative, then you are lower, or maybe, okay, because here it's similarity. So if the difference is negative, you are ranked higher. If it's positive, you are ranked lower. So because we can then calculate the rank, and in the recall we want the rank in the whole collection, and we also know how many ranks are higher of those, how many times the irrelevant one, the wrong class, was lower than yours. And it can be expressed as sum of these step functions. So now you can go for non-differentiable approximation by finding some efficient approximations of this sum and of this h function. So here the trick is very similar, like in classical neural networks. You replace a step function by some sigmoid, and you learn the parameters of the sigmoid. There are actually 2 sigmoids. It turned out that the one that compares individual scores and the one here should be different. And if we go through this, this is learned because on the training data we know the correct answer, and in the end we can derive a representation which actually ranks correctly better than the standard reference. Okay, I will go. These are technical things which are not that interesting, and again we tried it for different ranks, different data sets. The data sets are from either the nature or some cars and so on. Okay. So I will skip this technical, let's say just numerical results, and switch to another problem. So in classical textbook examples, we assume that the training data and test data are drawn from the same distribution. When we do examples like experiments, maybe in competitions, someone creates a data set and then really flips a coin and randomly sends things to the test and training. But this is very rarely the case in reality, that the test and training data are the same. I think it's almost never the case. So if you are doing, for instance, face recognition, then people age. And necessarily the training data will be older than the test data. If you are doing license plate recognition, and you, for instance, you will test your system in different places. Think about Poland. Between Warsaw and Krakow, you will have a different ratio of W's and K's, and the training data can represent some set of positions, but it cannot be optimal for all positions. If you are doing animals, identifying animals, some animals die, and so on. If you do what will show recognition of mushrooms, then they have seasons and things change all the time. So maybe the point is, look at the domain shift between the training data and the test data. It will always be there. And maybe the simplest example, which I'll talk about, is in the mushroom example, is the change in priors. So if you are picking mushrooms and you are developing a mushroom recognition app, you see that, for instance, the mushroom Boletus, that's the graph in the middle, does not grow between December and early June at all. So if you find a mushroom in April and the system tells you this is Boletus, it's wrong. Of course, when you are training the system, it had a lot of images of Boletus because this is one of the most popular mushroom species. And for some other mushrooms, it's the same, it's also different. So what does this show us? This shows us that the prior probability will be different at a different time of year, and now the question is, how do I handle that? You have two cases, one that you know these curves, and the second thing, you have to estimate it from the data. This is like a semi-supervised learning problem. So, for instance, if from the type of errors you make, you can estimate that, but this is beyond the scope of the lecture. The point is that if you know the priors, it's fairly easy under some conditions to use it to improve your classification. So this is an example from various artificial data. And it's supposed to show one thing, that very often you get training data or test data flat distribution. So someone says, we will be recognizing these 100 species. Here, there are 10 examples for each species. But if you are in nature, think about trees in the forest, okay? Spruce in Poland will be, I don't know, 100 times more common than a maple. And this will be even 10 times more than ash or some rare trees. So even in various competitions, the test and evaluation data are not the same. Now, if we train a classifier with cross entropy again, it's coming up here again, we might have a tendency to estimate, to deal with the output. This is here the output of the network as the probability for the given class. So, but observation from many papers is that a classifier, like if you want to treat the deep network as a classifier, it's not correctly calibrated. So what does that mean? Imagine that your deep network outputs after softmax for the 4 classes, so it will have 4 outputs, 80%, 15%, 1%, 4%. Now, if you are only interested in classical classification, you say, fine, 0.8 is the largest, I do class 1. Now, if your classifier was properly calibrated, that indeed, for cases that give you this output, you will have an error of 20%. So this is this means the output is indeed a probability. Now, it turns out that normally the deep nets are overconfident. So now, here we have the two concepts. Like, one is accuracy. So if you take 100 images and calculate the error, which means I take 100 images, and if I'm correct, this is ground truth, and this is my estimate, I add 1. So this is just the percentage of correct predictions. Now, what the bottom thing is the sum of probabilities of correct classification. On the long run, these two things should be the same. If you look what you get, and you take all the x's where all your images where your confidence was 100%, your recognition rate was 95. If it was 90, your recognition was 75. So the probability P was underestimating the success rate. So you need to deal with this, and there are two very simple methods called temperature scaling. It turns out that one simple change of parameter in the softmax can significantly ameliorate the problem. If you do not one parameter, but one parameter for, this is for the whole distribution, one more offset for each class, you get the state of the art, but this is an open problem still. And then, once you have the calibrated output, it's easy to take into account the prior probabilities. So this would be your decision that you would make if the data were distributed as in your training set. But now you know that the prior for a certain class on the evaluation is maybe 10 times more than on training. So this is a very simple rule. This is like well understood. So the point is that if you now want to take, want to take into account the change in the prior probability, you need to have a calibrated classifier. So the lesson is calibrate your classifier. Now, on many data sets, you do have, or in practical examples, you do have information about, I don't know what, one is location, one is space, and habitat. This is like forest, grass, dead wood. Month is time, and substrate is the type of soil. And all of those things get you an improvement in, it looks like small in a couple of percentage points, but if your error is 90% and you add 3% performance, then you reduce your error by maybe 20%. So what it says that very often in practical situations, you do have available some prior information, and if you calibrate your deep network, it's easy to exploit. The situation where you do not have this extra information and where the change of prior has to be estimated is more difficult, but that's also doable. And the last part I want to talk about, which is I think also neglected, is dealing with the loss matrix. So I'll show this on an example. Well, the application which triggered our interest to this problem was snake recognition. So in Northern Europe, it's very rare to be bitten by a snake and die. I think in the Czech Republic, it's something like 1 person in the 20 years. So there is this venomous viper, but it's actually not 100%. I think it's something like 20% if it bites you, and it's rare. But in India, you have 5 deaths an hour. So there are some specialist volunteers who are on WhatsApp watching, and they are getting images like, in India, someone was bitten by this snake. What is it venomous? What is this? What shall we do? Of course, it's difficult for these volunteers to be all the time alert, because here speed is important, so it would be nice to have something automatic. So if you look at the 4 most common snakes in India which are venomous, and the 4 most common non-venomous, and you build an app, you get quite decent results. You see that, so this thing is the reality, this is decision. So for most snakes, you get close to 100%, but for some of those, you get 2 or 5% error. And now it's important whether you end up in this red. So these the red squares is that you mistake a venomous snake for a venomous snake. Of course, this part is mistaking a venomous for non-venomous. That's lethal. This one means that someone who didn't need to get the antivenom will get it. And the point here is that if you treat this as a classical argmax problem, you build your, you go for your send the image, one of these images through your network, go for argmax, then you completely ignore the differences between the losses of your incurred by your incorrect decision. So we considered like 3 scenarios. The one is the one we do not, we shouldn't use in this case. but in many other cases where you say, okay, this is just a question of recognizing the species. The second one, you will say, okay, we don't care really about who is number one. We want to know what is the probability of being venomous. So this case already requires calibration for every input. Yeah, so even like we talked at the beginning, I talked about calibration of the top one, but for this to be really probability, the output for all of the classes has to be calibrated. You shouldn't be overconfident. And the case C is the one that we implemented in the end, is the one where you say, okay, if I make a mistake on venomous, it has a W times more higher cost than if you do it the other way around. Now this is a simplification because we are assuming, and this is partially true, that for certain groups of snakes you can, and especially often they are similar because they are in some genus, and similar even biologically, that you can administer the same antivenom and you'll be okay. So if we look at the numbers, we were able to train recognizer of snake species, which has the error of 2.1% of non-venomous being treated as venomous, and 1.9 on neglecting, or this is overlooked danger, not treating a venomous bite. Now, this is what you get if you train the classifier using classical cross-entropy. The cross-entropy tries to maximize the likelihood of the correct class, and it knows nothing about these losses. Maybe one thing, we are not talking about training here, we are just talking about correctly modeling the losses even with a trained classifier. Now, if we look at this table, it looks exactly the same, because if you calibrate for the top one, the calibration just changes monotonically the probability so that they are not biased, but what was first was still first. The top one was still the top one. The calibration didn't help you there. Now, this is the case B, where the case B is reminded here, we don't care about the top one. We don't recognize the species and then ask, is this venomous or not venomous? We just sum up over all classes the probability of venomous. And you see that almost no change. Yeah, so actually, this even led to a higher percentage of overlooked cases. Now, if you give weight, I'm not sure, I forgot to check whether it's 100 or 1,000. I think we put 1,000 on the cost of venomous. I think maybe this is, okay, so this is the same weight, but uncalibrated classifier and correctly calibrated. Because once you have the weight sort of multiplies the probability of the decision. So without calibration, you still are multiplying an incorrect number. So with calibration, we ended up with only 3 overlooked cases, but this is a huge number now. So it shows that if we want to push down this to 0, you would have to administer 60% of people who are bitten by a non-venomous snake, which is probably shows that we have to improve somehow. Even if we model things correctly, we have to somehow improve the visual recognition part. This one leads to 20 times more people untreated. It's still 0.1%, so it's 1 in 1,000, and 20% of people will get the treatment needlessly. So the treating, like properly modeling the loss function, maybe the penalty function, because this is different. I use the word loss at the beginning as what you optimize. This thing is the penalty calculated for the evaluation metric. By the way, one open issue is, if you know the weight, do you want to use it in learning or not? Because the weights, once you train some classifier, which then you calibrate, and the weights change, you don't want to retrain. So maybe we split the task by saying, learn classifiers which are then calibrated, and then only take the weights into account. Okay, now this just shows another example that how complex reality often is, that the loss could be even country dependent. So species have subspecies, and what is lethal in some countries is not lethal in other countries. So there is but also it's maybe encouragement for people that these days there are lots of very interesting data available, and often these loss functions, you think about them, oh, where can I get them? They are not available. Let's just get a data set with labels and let's do the classification. But in some sense, nobody cares about the class of the snake. You want to know whether you should administer antivenom and not. One more problem one more problem that we worked on is on mushroom recognition. More people get killed by that in the Czech Republic than by snake bites. So there are atlases which say like very tasty, edible but poor taste. So maybe this could be like a mushroom which is very edible, might have a price of 10 cents. This might be 1 cent. And then we go from the end, lethal, poisonous, potentially poisonous. Then you have some others which are like edible only if young and also taste poorly. So there the cost is something like, if you pick this mushroom, you can throw away everything that you've done the day. We ended up with a very interesting, in Denmark, used application which made, let's say, mushroom recognition more attractive. Lots of people started sending images. So in this type of citizen science where you make your model available, there is a very interesting positive feedback because you get lots of data. And then you have experts or even DNA analysis for the examples which were unclear. So maybe to summarize and finish the talk, in the deployment of machine learning systems, minimization of the evaluation metric is the goal. So align the loss with the evaluation metric and think about it as two different things. I also use the word deployment because often, I think in modern, let's say, use of machine learning systems, these training and test stages are not so separate as we think in, let's say, machine learning 101 class. Because often you get new data, you have domain shifts, you have to adapt to these domain shifts, priors change. So there are like two stages. One where you have usually a lot of labeled data, and then you have the deployment where you can get perhaps less data, but things are changing and you have to react to that. At deployment time, various domain shifts are common. Like domain shifts is a big, so I spoke about one domain shift which was the prior probability, but all sorts of shifts happen. So things like appearance of cars. If you try to detect cars, you might have a completely new shape of a car, and that one would not be detected. So that really touches to a problem that I didn't talk about, which is out of distribution detection. And if you think about it, probably every trained classifier should do as a first step checking whether the sample it is asked to make a decision on was represented somehow in the training set. So that, how can I be reliable if I can classify on things that were not in the training set? In this type of deployment, you will see it immediately, because the first thing that people do is that they start sending you photographs of mushrooms from a book, then they start sending you photographs of your dog. So you realize that the first thing, you have to do it anyway, because people will tell you, well, it decided that my dog is an amanita, and they will make fun of you. Okay, so The third point is that many pattern recognition problems can be solved optimally if you have this a posteriori probability of the class given x. This z means, and you take all other variables into account. So x is what you observe, k is what you care about, that's the class, and z are these like time of day, time of year. So for instance, if you do animal recognition, time of day is very important. So try not to be happy with some classifier, well, some deep network which has an output, and you take the argmax. For many problems, you try to use it as a method of approximating pk given x. And this is actually possible. So when I read this book a long time back, I was thinking, well, how can we get these probabilities? But now with generative models, you can push all sorts of data sets into Gaussian, into space where it is Gaussian. You can sample from it, which actually is a proof that these things work. And many of these problems are also open problems. So I gave some solutions, and probably any PhD student can see that none of this has any proof of optimality. These are problems where we address them in some way, but there are many other things to look into. So there's a lot of life besides supervised learning, give me the training set, send the function out, and hope for the best. Okay, thank you.